Hello, everyone, and thank you for joining me today at the Open AGI Symposium. I'm Zerui Cheng, an incoming third-year PhD candidate at Princeton University, and my advisor is Pramod. I'm thrilled to introduce LiveCodeBench Pro, our new benchmark for measuring deep algorithmic reasoning in large language models. The effort is the product of a dream team, ICPC gold medalists and world finalists who have faced the hardest competitive programming problems on the planet, experienced and professional problem setters who craft those challenges, and top-tier AI researchers whose work collectively span over 1,000 papers with 200,000 citations. This breadth of expertise ensures our benchmark is rigorous, fair, and grounded in real competitive programming practice. Among the authors, Wenhao, Shang, and Peiyao are also present at the event today. LiveCodeBench Pro has already gained traction in the community. It has been tweeted by top AI influencers, accumulating over 1 million views on X, and was covered in MIT Technology Review this June. This level of visibility shows the field cares deeply about robust, objective evaluation, and is a testament to our work. In brief, LiveCodeBench Pro is a contamination-free, high-quality competitive programming benchmark with expert diagnostics. Our top takeaways are: the first one, models lag humans on hardest problems. The solve rate on hard tier is 0% for any large language model. The second one is that large language models are far better at structured logic than creativity. And the third one is that external tools help a lot in boosting the score. Here is the agenda of the talk today. First, I will talk about motivation, what is competitive programming, and why it matters. Then I will analyze current gaps in today's competitive programming benchmarks. After that, I will introduce our main results and deep diagnostics in LiveCodeBench Pro. Finally, open questions and Q&A part. First, let's talk about what is competitive programming and what makes it unique in LLM evaluation. Competitive programming fuses advanced mathematics with flawless software implementation. Think of neat code on extreme steroids, pure algorithmic reasoning with no guessing. The problems span math, algorithms, and data structures. And success in competitive programming demands both deep mathematical insights and perfect code. Then let's briefly talk about why competitive programming is perfect for AI evaluation. Solutions of competitive programming tasks are usually evaluated on online judges, which provide 100% objective, fully automated evaluation, and there is no subjective grading. Unlike many AI benchmarks, there is no ambiguity in competitive programming. The solution either passes all hidden test suites under strict time and memory constraints, or it doesn't. And this makes competitive programming an ideal arena to truly test AI reasoning. And it is virtually impossible for a lucky guess to slip through thanks to the exhaustive test suites, which forces genuine reasoning, not random chance. LiveCodeBench was the first widely adopted competitive programming benchmark, and it has quickly become the go-to benchmark for Google, OpenAI, and Anthropic. It shows that competitive programming has become the de facto standard for measuring deep algorithmic reasoning in industry. As Olympiad medalists who are more proficient in competitive programming, we raise the following question. Is LiveCodeBench already good enough? And our answer is not quite. We have summarized the limitations of LiveCodeBench as follows. First, low differentiation. Top reasoning models cluster around 80% solve rate, while long reasoning baseline models clear over 65%. This narrow gap leaves little headroom for ranking models beyond a rough tiering. Second, no human baselines or detailed diagnostics. We also lack direct comparisons to humans in LiveCodeBench. What does an 80% solve rate really mean? Is it superhuman or just average for a CS undergrad? Without comparison to humans, we cannot calibrate model abilities meaningfully. And without diagnostics, we cannot pinpoint where models succeed or fail relative to human experts. Third, data contamination and liveness concerns. Benchmarks claim liveness by updating tasks every 3 to 6 months, but editorials and solutions leak online within days after the problems are out. So tools can scrape answers from the internet, inflating scores, obscuring true reasoning ability, and undermining claims of real-time evaluation. Then let's take a quick glance at our solution, LiveCodeBench Pro, that solves these limitations. To fix these issues, LiveCodeBench Pro offers 584 high-quality problems from Codeforces, ICPC, and IOI. Real-time capture and evaluation before any public solutions appear. Bayesian LO ratings directly comparable to humans. Fine-grained medalist crafted annotations of algorithmic categories and failure modes. Zero lead code content. Only the hardest and contamination-free challenges are included in the benchmark. They represent the boundaries of human intelligence in algorithmic reasoning. In LiveCodeBench Pro, problems are stratified by LO ratings, which means a contestant with the LO rating can solve the task with 50% chance in expectation. And there are 3 tiers in our benchmark. The first one is easy tier. These are problems with LO rating smaller or equal to 2,000. And world-class competitors can usually solve these problems within 15 minutes. The second one is medium tier with LO rating between 2,000 and 3,000. They usually combine multiple algorithms and require non-trivial reasoning. And the last is the hard tier, which are problems with strictly more than 3,000 LO rating, which corresponds to top 0.1% of contest participants, and some of the problems in this tier remain unsolved in live contests. Then let's do a quick reality check on the model performance. Here is where state-of-the-art large language models stand. The best model, O4 Mini High, has 53% pass at 1 on medium tier. No models can solve even a single task in the hard tier. And the LO rating of the best model, O4 Mini High, is 2116, which ranks around top 1.5% among human contestants. And in short, significant gap remains to human grandmaster levels, especially without external tools. Headline numbers trigger deeper questions. Where do models excel, and where do they break down? Then let's dive deep into the diagnostics. First, we categorize all problems by cognitive demand. The first one is knowledge heavy, which usually require templates and deep understanding of algorithms and data structures. For example, segment trees and fast Fourier transform. The second one is logic heavy, which usually demand step-by-step derivations. For example, dynamic programming and combinatorics. And the third one is observation heavy, which usually depend on aha insights that collapse the search space. For example, greedy algorithm and constructive tasks. Each category tests different cognitive abilities and represents distinct challenges for AI reasoning. Let's first take a look at the skill spectrum of LLMs. Plotting model rating across categories shows clear separations. Models excel on logic-heavy and logic-heavy tasks, but cluster lower on observation-heavy ones. LLMs are strongest on segment trees, dynamic programming, and combinatorics, but they are weakest on greedy, game theory, interactive tasks, and casework. They are precise and knowledgeable implementers, but lack creative leaps. Furthermore, our expert team performed a line-by-line analysis of 125 failed O3 mini submissions versus humans with similar ratings. And the findings are LLMs make 64% more conceptual errors than humans, misidentifying the right algorithm, yet make 63% fewer implementation mistakes once the logic is correct. Also, over 40% of failed submissions by LLMs fail on the provided sample inputs and outputs pairs, which is 5 times more than that of humans, highlighting missing self-verification and a clear area for improvement. On top of that, we found out that multiple attempts matter. For O4 medium, Perset 1 yields around 1793 elo, which is comparable to top 5% humans, while Perset 10 jumps to 2334 elo rating, which is comparable to top 1% humans, which is a huge performance gain. Most performance gains are made on observation-heavy problems by multiple attempts, because guessing and testing different hypotheses without rigorously proving can help. However, it's notable that hard-tail solve rate remain at 0% even with Perset 10, showing the lack in foundational capabilities of solving really difficult tasks. Also, it's worth noticing that even with Perset 10, there is a significant 400-point gap to the rating reported by OpenAI model card, and it highlights the power of external tools. Terminal access and web search explain the remaining 400 elo gap. Compilation checks, sample testing, brute force validation, and solution lookup all shortcut native reasoning, and again highlights the importance of liveness in evaluation. Without tools, native reasoning limitations become apparent, and with tools, models can iteratively debug and improve solutions. Finally, we compare DeepSeek R1 versus V3 and Claude 3.7 Solid reasoning versus non-reasoning, which reveals where explicit reasoning provides gains. Huge gains in combinatorics and data structures, but minimal or even negative gains in observation-heavy categories. It shows that current reasoning methods excel at structured logic, but fall short on creative insights. Finally, let's briefly summarize the key implications from our findings. The first one, claims of surpassing elite humans, which is unfortunately not true today, need serious qualification. Models excel at implementation precision, but not superior reasoning. Creative insights and observations remain uniquely human strengths. Claimed high performance largely driven by tool augmentation, not reasoning breakthroughs. And there is still significant room for improvement in edge case handling and algorithmic creativity. And finally, for evaluation, genuine liveness is very important for future benchmarks to distinguish native reasoning from tool use. In short, the gap to human grandmaster levels remains significant, especially in areas demanding novel insights and creativity. Then let's talk about open questions and start the discussion. Here is the roadmap for what's next in our project. Problem creation. Could AI craft novel, hard algorithmic problems, and how would we ensure their rigor? Model self-improvement. How might we enable models to test, critique, and refine their own solutions without human in the loop? And finally, a recursive RL framework. What would an end-to-end loop of problem creation, evaluation, and targeted improvement look like in practice? And that concludes the talk today. And thank you everyone for your attention. I hope you have all enjoyed the exploration of LiveCodeBench Pro with me. And if there are any questions. Yeah, please.
Very interesting work. You said that at hard, pass at 10 was still 0.
Yeah.
Have you tried increasing pass at 1,000, 10,000, 10 million? Like, does it ever pass?
We haven't tried it because we don't have enough funding.
But how high did you try? Just 10?
But intuitively, I don't think it will be true because we believe it is the lack of foundational capabilities that lead to the 0%. Or otherwise, the solve rate would be no, but not exactly 0. Yeah.
Were you able to analyze the failure modes for AI failures, effective algorithmic misclassification, boundary analysis, and stuff like that? Do you have further insights into that, especially for the hard problems?
Sorry, could you please repeat it?
Did you analyze failure modes?
Yeah.
In like hard problems, why AI failed? Is it reasoning, particularly algorithmic misclassification, boundary case analysis, or any other thing? Thank you.
For all the hard problems, the reasons for failure is conceptual errors. They cannot identify the correct algorithm, let alone implementation part.
Gotcha. So mostly algorithmic misclassification was the reason.
Yeah, and from our analysis, AI is very weak at identifying the correct algorithm compared with humans at the same level. Yeah.
Thank you.
This is very interesting work, by the way. So some people say that, the human can't beat the AI, which is what we're seeing here.
Yeah.
And, my question is, what if you allow the human and the AI to combine? Obviously, you're going to get a better score than the human being. Can you set that as a benchmark and then have the AI beat that?
I think that is already the case in some competitive programming platforms. Some humans, for example, top 5% humans use AI to help them in contests.
The human that you hear, they're already using AIs.
Yeah, in our project, the humans are not using AIs. The humans are experts who diagnose where AI is better and where AI is worse. And if we combine them together, I think AI is very powerful at the implementation. So once human gets the correct algorithm right, it will take AI a much shorter time to implement it correctly than let human write it.
Shouldn't that be the benchmark?
Yeah, I think that is the best that any human beings combined with any machines in the world that can do for now. Yeah.
One more question. Does these benchmarks generalize, like given different programming languages and stuff like that? Did you test this in one particular language? Did you try to apply the other ones?
We let AI select its favorite language. Usually, competitive programming is done in C++ or Python. Gotcha. And for hard problems, sometimes C++ is better because there's more high quality data in C++ in competitive programming.
So just to better understand, so the selection itself was also decided by the agents in this case?
Yeah, we let AI select its favorite language to.
And did you try to basically address, maybe use another language as well? Like just you know, did you try to repeat
we
it?
haven't do it systematically, but from my experience with AI, whether it uses C++ or Python doesn't matter because its scale of implementation is already very strong.
Yes, statistical, right, like depending on the training data available, it might actually change things. All right, thank you.
Yeah, thanks.
Okay, maybe one more question.
Hi, nice work. I have one quite detailed question. So I see your slides showing the gap between the R1 and the V3. And you mentioned that for some greedy or game theory, the observation heavy related topic problems, there's not too much games. Actually, it's quite counter to my intuitive because for the reasoning model and the non-reasoning model, usually in their papers they mention that the reasoning actually activates their abilities to summarize, to do a self-reflection, and to come with some new ideas. But actually, it looks like it's not. Do you have any intuition on why this happens?
I think for the observation problems, which usually doesn't have a very high error rating, they require some observations or some intuitions, but these are not easy to find a very generic pattern in it. So that's why AI, although with a lot of data, but cannot identify the patterns and the underlying observations. Yeah.
All right, I think those are all the questions. Thank you again, Zerui, for a wonderful talk. Thank you.
Thank you. And here is my contact information. So thank you so much.